Alright, so here we are with the quiz review. We're talking about part 2, yes. Okay, so we're going on to number 42 from the previous assignment video. Oh, that's bad. Alright, and we're graphing natural log of x. So if we take a look at our graph, it goes through at 1, and then we have an asymptote at our x equals 0, or the y-axis, and then, oh man, it goes back down again. Okay. So it goes from its asymptote down here to a maximum point that I can't quite tell. Oh, there it is. At 2.7. So that's about here-ish. And then goes back down. So a little more exaggerated, the idea is that it goes up and then kind of back down. So there's this maximum point here. So this maximum point has a coordinate of 2.718, 0.368. And we'll use that. And so then it does also have a horizontal asymptote of y equals 0. So, wow, lots of asymptoting happening. Okay, so first thing we'll do is our domain, and the domain in this one is going to go from 0 to infinity along the axis there. Our range, the lowest point is negative infinity, and the highest point is going to be our maximum, which is at 0.368. You don't want to put the x value, you want to put the y. And then we are asked if it is continuous, and we're going to say that it's continuous on its domain, because of course there are asymptotes on it, but it doesn't jump when you do actually draw it. Then we're looking for increasing and decreasing. So increasing is actually oh wait, no, it's increasing from 0 for our x to the maximum point, which is at 2.718, and then it's decreasing from 2.718 to infinity. There it is. Alright, then our next question is if it's symmetric, and it is definitely not symmetric, meaning there's no rotational or point cut in half. And then symmetry boundedness, it is bounded above at that maximum point. Alright, then we're looking for extrema, and of course we have a maximum value, a local maximum at 2.718 and 0.368. It has asymptotes, lots of them. Okay, so we've got a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. And then we get to identify our end behavior. So let's see, the limit as x goes to 0 from the right, so that's what's happening here, of the function is negative infinity. And then the limit as x goes to infinity of the function is 0 for that asymptote. Interesting. Okay. So then we move on to our graphing calculator addition here. We're going to find an exponential regression and a logistics regression for this data. So once you put it in, well, it's for both different states, so it doesn't matter, but find an exponential regression. So that's going to be your exp reg in your stat button and calc. And then we want it for Georgia's, so we want this to be our list 1 and this to be our list 2. And because we're talking about exponential, you can do it years since 1900. That will help you out when it comes to writing the equation, because it's going to be huge numbers if you don't reduce it by 1,900. Alright, and then we're going to use it to predict the population in 2005, which is technically 105. So just to be clear, that doesn't look like a 105. There we go. That really doesn't either. Okay, so we're going to stat and then edit in order to put our list in. So you put them into your list, got it, and now we get to calculate the exponential regression using list 1 and list 2. So our equation is going to be in the format of ab to the x, and our a value is 2.0956, and your b value is going to be 1.0122. There. Then we want to use it to predict the population in year 105 or 2005. So we're just going to put a 105 there, which means that we'll take 1.0122. I'm actually going to do the exact decimal to the 105, well, the decimal that they give you, and then times 2.0956, and we get a population of 7.47, and I believe we're in the millions. It's a little interesting doing population predictions at this point because of coronavirus, so yikes. Okay. There's a downer. Alright, so find a logistic regression model for Illinois. So now we're going to do the same thing, but now for Illinois. So Illinois is list 2. So going back to our edit after stat edit. And so if we do our list 2 as Illinois, and then go to stat calc, and then go to logistic, the equation is going to pop out as c over 1 plus ae to the negative bx. So it's plugging in that equation. And so our logistics output is a c value of 14.3614 over 1 plus an a value of 2.0083 times e to the negative b, which is 0.0249, times x. And then they want us to find when it's 2010. So 2010 is 110 instead of 105 like the previous problem. So we'll put 110 in for this x, which should not be as bad as if we had to work it backwards to find out when the population would reach. So we're going to do negative 0.024. I'm going to do the whole decimal that I can see. 849 times 110. And then we're going to do e to that decimal. And then we're going to multiply it by 2.0083. We're going to add 1 to that, and then we'll do 14.3614 divided by our result. So apparently we're going to have 12.7119 million people in 2010, which seems to be working. Okay. So then we move on to population decrease, and apparently in Metroville it's 123,000 and is decreasing by 2.4 each year. So we need to write a function that models that, and so of course it's going to be in our ab to the x format, where b is going to be a 1 minus the rate, because we are talking about decreasing. So our equation is going to be, for part A, y equals our starting value of 123,000. And then we'll multiply that by our b value of 1 minus 0.024. That's the decimal equivalent of 2.4% to the x. Which, of course, that decimal can be rewritten so that we don't have it sitting there, but 0.976. And then we want to predict when the population will be at 90,000. So that means that y is going to be 90,000, so I'll do a little algebra over here. So 90,000 is going to equal 123,000, 0.976 to the x, which means that we'll have to divide by 123,000 to both sides. So we get 0.7317, and then that's going to equal our 0.976 to the x. And then to solve this, the easiest way is to rewrite it from exponential to log form. So we're going to have log base 0.976 of 0.7. Let me think about it. Of x. Backwards in my head. Nope, of the 0.7317 is going to equal x. Alright, so in that case I just need to do log base 0.976 of 0.7317 in the calculator. And so remember that's over in your math key, and so the decimal equivalent of this guy here is 12.86, and that is the years, so in 12.86 years, so during year 12. Alright, then the next one talks about the population in Preston is apparently 89,000 and is decreasing, so 1 minus 0.018 per year, and 1 minus 0.018 is 0.982, just so that we have that for reference. And so the function that we're going to have is y equals 89,000 times 0.982, that decreasing rate, to the x. If we want to predict when it's 50,000, we set that equal to our original equation found in part A. Divide by your 89,000. And 50,000 divided by 89,000 is 0.5, that's sloppy, 0.5618. And that's going to equal our leftovers. And so if we rewrite this as log, it's going to be log base 10.9, oh, I thought that was a 1, it's a parenthesis. Log base 0.982 of 0.5618, and that's going to equal x. So apparently we're going to have that population in 31.74 years. Okay. Barring any pandemics. Okay. And that is it for the review. So hopefully we are ready to try out a quiz.